So what we're going to do now is we're going to talk about how Java parallel streams works under the hood. And this is kind of a down payment to a longer discussion we'll have a little bit later, probably on Wednesday, where we'll go into more detail about how streams works. But I want you to at least have a good understanding of what's going on, because it'll help you to make informed decisions about when to use parallel streams and what to expect when you apply it. And there's a nice article by Brian Getz here at this link at the bottom of the slide that goes into more detail about some of these things. So a Java parallel stream implements a variant of the MapReduce paradigm that's optimized for multi-core processors. You can use MapReduce in different contexts. You can use it in cluster computing, which is commonly where it's used for groups like Google or other computations that do lots of parallel searches and then combine the results back together again. In the case of Java streams and Java parallel streams, it works on a single processor, ideally with multiple cores. And here's a sort of a whimsical example to illustrate how MapReduce works. So you might have a refrigerator full of all kinds of different produce and food and so on, and you could go ahead and take each of the items that you want to make into a sandwich or sandwiches. So you have like a loaf of bread, a head of lettuce, a block of cheese, a tomato, some meat, and so on. And then you could go ahead and do the partition phase where you take those things and you put them out there so they can be processed in parallel, perhaps by different workers at the restaurant. And then you do the map phase where you do some processing on each of these things. You slice the bread and go ahead and shred the lettuce and chop the cheese or cut the cheese or whatever you're going to do with the cheese. And you chop up the tomatoes and the meat. And then the reduce phase is where you would take those little pieces and you'd put them together into a bunch of tasty sandwiches. So you could imagine having groups of people that were doing that different computations, those different tasks in parallel. And so you could, at least in some sense, get more sandwiches made with a group of people using the MapReduce-like model. With parallel streams, as we've seen before, there's actually a three-phase data processing strategy called split, apply, combine. And we'll go through this again very quickly and go in a bit more detail than we did the first time we talked about it. So as you can see here, you've got your data source that'll be split up into atomic-sized chunks. There's a bunch of processing that takes place in parallel, and then we join the results together. So let's talk a little bit more about each of those phases. So the split phase, as the name implies, will recursively partition an original data source into a bunch of chunks or sub-data sources or sub-tasks or whatever you want to call these things. And that, of course, is just classic divide and conquer. You've all learned to divide and conquer with quicksort and heap sort and merge sort and all those good things that you undoubtedly learned about in your algorithms class here, wherever you took it, either here at Vanderbilt or elsewhere. And so I kind of think about, taking a pizza and slicing it up into different slices. Each chunk that's created with the split phase is independent and atomic. So it's basically a set of subsets of the original data source, and each one ideally will be independent of each other, so there's no dependencies, which makes things work better for embarrassingly parallel reasons. The way this happens under the hood, of course, with parallel streams is by using splitterators. So splitterators will be used to partition, say, collections in Java up into their atomic-sized chunks. And the way that the splitterators work with the collections that come out of the box, like array list and hash set and so on, is they split them up into atomic-sized elements of size 1. So they keep recursing till you get things that are size 1. And that's where everything starts. You could write your own splitterators that would not go down to size 1 if you wanted to. Probably unnecessary, but you could do it if you felt like it. And the way that this works under the hood is that there's a TriAdvance method that gets called back in order to kind of move things ahead. And that's what's used by sequential streams, or it's used by the sequential processing part of parallel streams. And then there's also another method called TriSplit, which is used only for parallel streams. It's what's used to partition a chunk into subchunks. Ideally split evenly and ideally split efficiently, as we'll talk about. Each Java collection has a splitterator, as you can see here. So the splitterator is what's used to split things up. And it is inherited from the collection interface, but then almost invariably customized for each different kind of collection. You are capable of defining your own custom splitterators if you so desire. I am not going to cover this in great detail in this course because we have lots of other things to cover. But if you're interested in learning about how to do custom splitterators, I have some other material on my website from previous versions of this course where we were not we were doing things in a different way that talk about custom split iterators. So if you're curious, you could take a look at, say, last year's 2020's version of this class. This year, we're going to include a lot of other stuff on other topics, so I don't want to belabor things we're not going to cover in detail. As I alluded to earlier, parallel streams perform better or perform best on sources of data that can be split efficiently and evenly. And a great example of this would be an array list. An array list is very easy to split evenly and efficiently because it takes constant amount of time to find the midpoint, and you don't have to do much work to split it. You just basically update some indices and away you go. Other data structures like a linked list are much more complicated to split efficiently and split evenly. The next phase is the apply phase. So as we are breaking these chunks up, not after, but as they're being split up into chunks, those chunks are being fed into the common fork join pool, which is what Parallel Streams uses to do its computation. And there's a reason it uses the common fork join pool. And that reason is because that way you can have one point in your process where ideally all the parallel tasks will be enqueued so that you can do a more efficient job of doing global balancing of load across the different processor cores. So putting them all in one place is actually a big win as opposed to partitioning them up into different sub-chunks or sub-pools. Splitting and applying can run simultaneously after certain limits are met. It's not split everything and then start to apply. So as you're splitting, you can start to apply as well. And that does a better job of taking advantage of the inherent parallelism in the system. Under the hood, it uses this fork join pool framework, which we will talk about in more detail later. It's basically a way of maximizing processor core utilization through the concept of work stealing. And we'll talk more about work stealing when we get to the common fork join pool and how it works under the hood. But it's very, very cool, and it's really meant to supercharge the processing of your system by making sure if there's work to be done, then a core is off doing that work. So cores don't just sit by idly waiting for things to do. They're aggressively going out and stealing work from other threads so that they can get more processing done per unit time. You, the application developer, you, the application programmer, can control the number of threads that are in the common fork join pool. This is a little known fact. We'll talk about it later when we get to this Parallel Streams internals lesson, but you can actually control the size of the pool. This is a source of a lot of confusion. People don't think you can do this, but you can quite easily do it. And you use something called the managed blocker in order to do that. And then the third and final phase is the combined phase, where we take all the partial results, excuse me, and we join them together sort of recursively, or working out of the recursion to get back to where there's only one single combined result. And this is typically done by terminal operations like collect or reduce, which we have talked about and we'll talk about more later. You can have different kinds of collectors that are used if you're doing collect, and those collectors can either be concurrent, in which case you are responsible when you write the collector to make sure that you synchronize access to some shared mutable result container so it doesn't have corruption and race conditions and atomicity problems and so on. Or you can also make your collectors be non-concurrent and non-synchronized. And then the Java Streams framework will arrange to make sure that everything gets merged together without having to worry about race conditions. We won't spend a whole lot of time talking about this right at the moment, but we'll touch on it probably next time because it's very interesting. And of course, you can also define custom collectors if you want. And once again, we'll talk a little bit about that when we get to the Parallel Streams internals, but there's other sources of information on other earlier versions of this course if you're curious about how that works. So that's a quick overview of how Java Parallel Streams works under the hood. Again, we'll cover this in more detail a little bit later, but I just want you to get a good sense of what's happening so when we talk about the example that we're going to come up with here shortly, all the pieces kind of fit together.